So one final question we can consider is that can we always be able to integrate any function? And to answer this, well, we kind of have a certain class of functions that are called elementary functions. And this basically includes everything that we've studied so far. Polynomials, rational functions, power functions, exponential functions, logarithmic functions, trigonometric and inverse trigonometric functions, hyperbolic and inverse hyperbolic functions, any function that can be expressed or obtained through addition, subtraction, multiplication, or division and composition of these types of functions. So basically anything that we've studied so far is an elementary function. And here's just an example, right? The square root of x squared minus 1 over x cubed plus 2x minus 1 plus natural log of hyperbolic cosine of x minus x e to the sine 2x. Right? It's just some combination of all these various things. But you see that, yeah, this kind of incorporates a lot of different types of functions that we've studied so far. So these are elementary functions. And what we've noticed is that we basically have rules for taking the derivative of any elementary function. So if f is an elementary function, then f prime is also an elementary function. But when we compute the integral, it's not necessarily going to be an elementary function. Okay? And here's a classic example. Consider the function f of x equals e to the x squared. Clearly its integral exists because you can define the function f of x equals the integral from 0 to x of e to the t squared dt. And so this function, whatever it is, would be the antiderivative of e to the x squared. But notice it's expressed in terms of an integral. And what we would need to do would be to express this in terms of an elementary function. So, I mean, just trying to find an antiderivative of this would be difficult. We won't go into it in any detail here, but the idea is that we can't actually find an elementary antiderivative of this function, even though it clearly does have a derivative. An elementary antiderivative of this function does not exist. Even though, of course, it is differentiable, it is not, and it is continuous. So it's not to say that the integral doesn't exist, but the integral is not something that can be expressed as an elementary function. It could be expressed in other ways, and we'll see other ways of doing that, for instance, in terms of an infinite series, or through numerical approximation you can evaluate it. But yeah, in general, right, not every function has an antiderivative. And so being able to integrate, or being able to find the integral of a function, is not always possible in the methods that we've had so far. Here are just some other simple examples. Again, these are ones that you can't find an antiderivative for, or you can't find an elementary antiderivative for it. Okay, so if you stumble upon one of these integrals, you might sit there and try and find a technique for solving it, but it would be futile because the elementary antiderivative for these functions actually does not exist. Okay, and when you come across one of these, of course, you probably won't see it in one of the sections here where you're asked to find an integral, because it's not possible. But later on, when we look at maybe approximating using numerical methods, we might be able to evaluate a definite integral of one of these kind of functions. So that'll be something we'll need to consider in a different section.